Magnetism. Magnets are pretty amazing, and they're used in everything from car engines to computers, and of course, they hold your latest report card or artistic masterpiece on your family's fridge. But how are they made and what are they made of? Really, what's in a magnet? Well, that depends on whether you're talking about a natural magnet or a man-made magnet. Natural magnets come from a piece of magnetite called lodestone, but the magnets that we see today are created or man-made. There's a group of materials known as ferromagnetic materials, and this group includes iron, cobalt, nickel, and some alloys of some rare earth elements. Today, when we say something has magnetism, we are referring to its properties and interactions of the magnets. Since elementary school, you have played with magnets and noticed that two magnets exert a force on each other. Depending on which ends of the magnets are close together, the magnets either repel or attract each other. You might even have noticed the interaction between those two magnets can even be felt before the magnets even touch. The strength of the force between the two magnets increases as magnets move closer together and decrease as magnets move farther apart. This force you are feeling is the magnetic field that surrounds the magnet. Magnetic fields exert a force on other magnets and objects made of magnetic materials. Now, of course, the magnetic field is strongest closest to the magnet and weaker further away. Any fields also have directions, and the directions of the magnetic fields around a bar magnet are also shown in this diagram. Looking at these diagrams, you notice that the magnetic field lines are closer together at the ends of the bar magnet. These regions, called the magnetic poles, or where the magnetic force exerted by the magnet is the strongest, and we call it the north and south pole. For bar magnets, the north and south poles are at the opposite ends. Two magnets can either attract or repel each other. Two north poles are going to repel, like poles repel, right? Same with south poles, they're going to repel. But one north pole and one south pole, which are unlike poles, are going to attract each other. When two magnets are brought close to each other, their magnetic fields combine to produce a new magnetic field. As we said earlier, only a few metals such as iron, cobalt, and nickel are attracted to magnets or can be made into permanent magnets. But what makes these elements magnetic? Remember, every atom contains electrons, and electrons have magnetic properties. And in the atoms of most elements, the magnetic properties of the electrons cancel out. However, in the atoms of iron, cobalt, and nickel, these magnetic properties don't cancel out, and each atom of these elements behave like small magnets and have their own little magnetic field. The magnetic field created by each atom exerts a force on other nearby atoms. And because of these forces, large groups of atoms align their magnetic poles so that almost all the poles point in the same direction. The group of atoms with alignment at poles are called magnetic domains. Each domain contains an enormous number of atoms, yet the domains are too small to be seen with the naked eye. So, ask yourself, let's say, take a pair of scissors. A pair of scissors contains iron, so why aren't these scissors behaving like a magnet? Well, even though each domain behaves like a magnet, the poles of the domains are arranged randomly and point all in different directions. As a result, the magnetic fields from all the domains cancel each other out. However, if you were to take a magnet and take that pair of scissors, if you take the magnet and stroke it down the scissors in one direction about 20 times, now, this is going to line your magnetic domains up in the scissors. Now take your scissors and see if you can pick up some paper clips with it. You can. You have just created a temporary magnet. Now, it's called temporary because if you drop the scissors a few times, cut with them and use them a little bit, eventually you're going to scramble all those magnetic domains up again and it's going to lose its magnetic property. But that's pretty cool, right? Okay, it's time to show what you know.